In this video, we will discuss the factors that affect the solubility of gases. We may not realize it, but many solutions we encounter contain gases as a solute. A common example is club soda or soda pop. Our blood contains dissolved N2O2 and even carbon dioxide gas. In fact, the dissolved oxygen in lakes, rivers, and oceans help to sustain aquatic life. If the concentration of oxygen dissolved in a body of water is too low due to the decay of organic matter, it can undergo eutrophication, which essentially means that the body of water has died and can no longer sustain aerobic organisms. So you can see that the solubility of gases is an important environmental concern and is a common phenomenon we come across in our everyday life. If we take a closer look and observe the molecular image of club soda, we can see that the carbon dioxide is homogeneously mixed with water molecules. The solubility of a gas in a liquid, such as CO2 and H2O, depends on both the temperature of the solution and the pressure of the gas. To help understand the effect of temperature, you can consider this club soda or any of your favorite soda pops. If you have ever had a glass of soda that wasn't cooled down before you drank it, you might remember that the soda was very fizzy and many bubbles were present. In comparison to a cold soda pop with less fizz, we can conclude that many more gas molecules are leaving the solution at a high temperature. Another great observable example is how the heating of room temperature water on a stove leads to the formation and eventual escape of gaseous bubbles right before boiling. Again, an increase in temperature has led to less gas molecules in solution and therefore decreased solubility. This solubility curve for gases as a function of temperature helps us to quantify the relationship that we have just discussed. For all gases, the solubility of the gas in a liquid decreases as the temperature increases. In other words, the solubility of a gas is inversely related to the temperature of the solution. The other factor that affects solubility is the pressure of the gas. Consider a can of soda pop which is closed to its surroundings. Within the can, the pressure of carbon dioxide is high and therefore majority of the CO2 is dissolved in the solution. However, when the soda pop is open, the gas molecules have room to expand, therefore reducing the pressure within the can. This causes the gas molecules to bubble out of solution, resulting in fizzing of the solution. From this example, we can conclude that the gas molecules remain soluble in solutions at higher pressures. In other words, the solubility of a gas is directly related to the pressure of the system. To elaborate upon this concept, we can consider a gaseous solution in a closed system. The gas molecules in the system are in equilibrium between their gaseous and dissolved states. Remember that equilibrium is not static as the current picture depicts. The gas molecules are entering the solution and the gas molecules in the solution are exiting. At equilibrium, the rate of this exchange is equal. However, if we decrease the volume of the closed system, in other words, increase the pressure of the gas molecules increases, causing the rate of the gas molecules entering the solution to rise. This causes the system to re-equilibrate, however, leads to more gas molecules dissolved in solution. The equation S sub gas is equal to K sub H times P sub gas is known as Henry's law. It allows chemists to quantify the solubility of a gas, represented by S sub gas, at a certain partial pressure of the gas, represented by P sub gas. The solubility of the gas is dependent on its identity, which is reflected in the Kh, or the Henry's law constant. This table provides the Henry's law constant values for some various common gases in water at 25 degrees Celsius. Notice that the units of Kh are in molarity per atmosphere. Therefore, when solving for the solubility of a gas, you need to make sure that the partial pressure of the gas is in units of atmosphere. The units of atmospheres will then cancel out and leave the solubility of the gas in the units of molarity. Let's practice a problem where we'll need to apply Henry's law. We are asked what pressure of carbon dioxide is required to keep the carbon dioxide concentration in a bottle of club soda at 0.12 molar at 25 degrees Celsius. Because we are discussing the solubility of a gas, we will use Henry's law to solve the problem. In this scenario, we are actually asked to find the partial pressure of the carbon dioxide in the bottle, but we are given the molar solubility. We can rearrange this equation to isolate our variable, piece of gas, by dividing by Kh on both sides. Therefore, the solubility of the gas divided by Kh will be equal to the partial pressure of carbon dioxide. In order to solve for this value, we must know the Henry's law constant for carbon dioxide in water at 25 degrees Celsius, which we can look up in our book as a reference. The table here indicates that the Kh constant for carbon dioxide is 3.4 times 10 to the negative 2 molarity per atmosphere. If we plug in the Kh value in addition to the solubility of the gas, which was provided as 0.12 molar, we can see that the units of molarity will cancel, and therefore we determine that the partial pressure of carbon dioxide would need to be 3.5 atmospheres. So overall in this video, we have learned that the solubility of gases is inversely proportional to the temperature of the solution, but directly proportional to the pressure of the gas. We can specifically quantify the solubility of a gas as a function of the gas's partial pressure by using Henry's law.